So obviously we can do some examples of the revolving stuff, but the first thing I want to do, bless you, is look at the last section real quick of chapter 6. It's the easiest little section in there. It has to do with finding the average value of a function over an interval. And really, if you think about it, how do you average anything? How do you average a list of numbers? Add them all up. Divide by how many there are, right? So I'm going to come back to that definition at the end of what we do here. This is 6.5, the average value. I just want to do this section real quick. So if I ask you, if I have something going from, let's say, 1 to 5, this triangle. Let me ask you this first. All right. This is a skill you got to have in the first place. Can you please find the equation of this line? It's a straight line. Take a minute and find the equation of that line. So take a step back into Math 90. Why not? All right, goes to the points 1, 0, and 5, 6. So it's the slope 6 over 4. So let's go ahead and use this one. Y equals 3 halves x minus 1. So y is 3 halves x minus 3 halves. To check it, if I plug a 5 in, 3 halves of 5 is 15 halves, minus 3 halves is 12 halves, which is 6. Yeah. Yes. All right. Now, let's just keep that on side for a second. I'm going to double check what we do. This is a simple shape. Integration finds the area. Okay. So another way to look at this average value, the average value of this function, it would be the average what of the triangle. The average value this function takes on. What's this function go from to? It goes from 0 to 6 over the range of 1 to 5. So like a good guess for the average value would be roughly 3, right? Why? It's in the middle. So the average value of a function is also known as the average height that the function gets up to. Is how far it goes from a height of 0 to a height of 6. So a height of 3 sounds about right for the average value. It has to deal with how far it goes over, though. So the best way to see why it gets set up the way it is to relate it to the area, which is why an interval pops up. And then I'm going to talk about it in a different way, back to what we think of as average in general for any numbers. So let's just do this 2 ways. Let's do this geometrically. What's the area of this triangle? 1/2. One half of the, 6. 4 equals 12. All right. Now watch, this is kind of cool. So the area of this thing is 12. If I could chop this off and move it, if I could basically squish it, and these are like, I can't change how wide it is, but I can mush it down so it becomes even. Wouldn't that be the average height? So So I'm really just rearranging the area. So I got to keep this width the same, but I'm basically trying to put this here so it becomes this equivalent rectangle. And what's the area of the rectangle? It has to be the same as the area of the triangle. So what's the area? So here's the area of the triangle. If what do I do with this to see how tall the rectangle would be? Well, what's the length of the rectangle? 4. And what's the area of the rectangle? 12. So what's the width of the rectangle? 3. So this is the area divided by the interval here, right? The b minus a. Is that cool? That's how you get it. Why? Because if I get the total area of the thing, and then I divide by this, that would be the height, or the width of the corresponding rectangle, which would be the average function height. It's almost, I love this. So here, geometrically, I just get 12 divided by 4, so I get 3. Let's do it calculus-wise. How would calculus get the area under this function? What's the area under this function using calculus? Integral from? No, what? 1 to 5. What's the function?
3/2.
Yes, 3/2 x minus 3/2. All right, do that real quick. Catch up to you guys. So when I plug a 5 in again, 75 fourths minus 15 halves minus 3/4 plus 3/2. Is that cool? When I put the 1 in, I got to subtract so the signs change. This is the area, remember, by the way, so we're not quite getting the real answer yet. We're just focusing on the interval right now. Right? Because I'm going to have to take the area and divide it. Right? We're just finding the area a different way. So this would be 72 fourths, which is 18. Minus 12 halves. So again, the area is 12. Okay. Now, real quick, I always have somebody who's like, why the shit would you ever do this? This was so much easier. Well, of course this is so much easier. Stupid rectangle, stupid triangle, right? We're going to have stuff that's like, and then you bring some geometry, too. So I made a nice simple example so we could have done it. We could just do it straight up in geometry. Here's the calculus agreeing with what the shit we got already, which is always nice to verify that calculus is true. And then how do I find the same way? I just divide by 5 minus 1. So I'm going to get the same answer, right? So the general way to find the average value of f of x on a to b is 1 over b minus a. Divide by the length. Find the area. That's how you find the average value of a function. Now, why does this jive with our regular idea of average? Well, if I have a function from 1 to 5, how many values do I have to add up? Remember, how do you find the average? You add them all up, and you divide by how many there are. Well, how many values do I have between 1 and 5? How many outputs are there? Infinite number. So what's going to handle an infinite sum? A frickin' integral. And then if you divide by how far they go, that's like dividing by how many there are, right? So this still kind of jives with the idea of average of a set of numbers. The integral handles the infinite sum part. How are we doing? There's two different really cool ways to look at that I was never shown when I learned this. So appreciate that shit. All right, so section 6.5 is like breath of fresh air after rotating things. And it's really nice, little palate cleanser. That's really, oh, there's the 6.5 right there. Okay, so real quick, more people came in. Anybody else need practice test? Yes.
For this test, are we itemizing the substitution values for the non-sums? Or the limit definition that you do?
Yes.
Just so like the...
You need to know that.
N
So,
times N plus 1.
what do you mean? Oh, those. No, I'll give you those.
Oh, okay.
All right, I will give you the sum of I squared, the sum of I cubed, right? You don't have to memorize those, but you do have to memorize the limit as n goes to infinity, summation, yeah, the form of it. But I'll give you you don't have to memorize the sum of I cubed, right? Yes?
Can you run through one of those problems?
Sure. So let's see. All right, so find the area under this on the interval using the limit definition of areas. So try to write this down. I'll start it off. You guys try to finish this out. Write the rest of the form down. Okay. Sum I equals 1, 2, n. Height times width, right? It's just a rectangle. So height. The height is f of xi. Come on, the function value is almost always the height. That's how tall it goes. And the width, of course, is delta x.
Delta x.
Because this is a big step, not an infinitesimally small step. This is a finite number of rectangles. This allows it to go to infinity, but right here it's a finite number. So this is a gross step. It's a large step. So now I kind of know what I need to figure out. There's three main things I need to figure out. You're figuring out what delta x is, what xi is, and then what f of xi is. And I throw all this shit in there. So how do I figure out what delta x is? In general, what is it? Over n. There's delta x. xi in general is a plus I delta x. Where I start plus how big each step is times the number of steps. So just fill in it. What's xi then? Where do I start? 1. I times delta x is 2I over n. Okay. And then what's f of xi? It's going to be 2 minus this stuff squared. So then we just kind of do this real quick on the side. So I don't have too much shit going on. So if I FOIL this out, it'll be 1 plus 2i over n, 2i over n, so 4i over n. And then 4i squared over n squared. Is that cool? You do that work on the side, so you don't have to worry about it while you're doing the other shit. So I throw all this stuff in here. So then I got 1 minus 4i over n minus 4i squared over n squared times delta x. And one of the biggest mistakes is people put this in there. Here's delta x. Otherwise you get an extra I, which is always freaky. You have an extra I running around. What am I going to do next with this?
Try to isolate the I.
True. So I'm going to break this up into 3 sum problems inside of a limit. So I've got the sum 2 over n. So really, are you guys? Let me see if you guys are cool. That can come out front. Minus. See if we can all handle this. This will be 8i over n squared. The 8 over n squared can come out front. Is that cool? Because like Gabriel said, you want to get the I stuff by itself. That's the only variable according to the summation. N is a constant as far as the summation is concerned. That's why it can come out. That I can't come out. And the last guy, what's he going to be? Eight over, careful.
8 over n?
And cubed, sum of I squared. Now what do you get when you add 1 up n times? When you add 1 to n times. Not when you multiply 1 n times. When you add 1 n times, you get, I love you guys so much. You get n, of course you do. If you add 7 8 times, you get 8 times 7. Right? If I add 1 n times 1 is n. Right. So here, all right, so now I can start doing these summations. So I got 2 over n times n. Anybody remember what the sum of I was? Yep. And so this is what I'll give you. And the sum of I squared is the really freaky one. Let's see if I remember it. I don't. N plus 1 times 2, I can't remember. See, that's another reason why I don't make you memorize these, because I never did. It's over 6. 2n plus 1. Nobody can look that up for me? You guys are so nice. You got it? Oh, here it is. N times n plus 1 times 2n plus 1. Okay. So here's the steps. You figure out the 3 big pieces of this, throw them in, Get the I stuff by itself. Take out everything not related to I, so they can really see what you're dealing with. I'm going to give you this stuff. Plop those in there. And now what can I do? What's enabling me to do something with the N stuff? The fact that I have this limit. Now here what happens?
Cancel each other out.
Yeah, 2. Here what happens? What's this limit?
That's n squared plus 1. Or n squared plus n.
So this limit here
Uh-huh.
is 1, because the coefficients are 1 in front of the equal degrees. Is everybody cool with that? Is everybody cool with that? That should be 0 problem. Right?
Isn't the coefficient 2?
Huh?
The coefficient be 2?
This is 1, and then what do you have here? 4. Okay, I like it. So you can treat them, I can just leave the constants out. I just looking at the end stuff. And the constants are just kind of floating there waiting. So I get minus 4. What happens here? What's this limit? You can do it. If you did, multiply this out, but don't. If you did, but don't. If you did, what would be the n cubed piece? It would be 2n cubed over n cubed is 2. So that limit is 2. All that matters is the highest degree term, because the rest of it is shit. So what do you get here? You get 16 over 6, which is a over 3. So then you get whatever that is. Negative 14 thirds? So check it real quick with an interval. Integrate that. Check it. Integrate the situation. Check it.
Negative 14 over thirds.
What is it?
Negative 14 over thirds.
Sweet. It's always nice to have verification. Now, if right now you cannot set this interval up that I'm asking you to calculate, you should be worried. What's the interval going from to? What's the interval going from to? 1 to 3. And what am I integrating? Yes.
Yeah.
So that's the interval that represents this situation. Where's this symbol come from? This symbol represents this, right? It's the infinite sum. So it's the integral of the function dx. Because what happens with delta x when I have an infinite number, it goes to infinitesimally small, which would be represented by dx. Delta x is bigger than infinitesimally small. So what's this integral?
Would be 2x.
From 1 to 3, so when you throw a 3 in, you get 6 minus 9. And when you throw a 1 in, you get 2 minus 1/3, so it'll be plus. So I get negative 5 plus 1/3 is negative 14 thirds. Yeah. Check. Of course, this was quicker, right? That's because this was discovered and used before we made the connection to antiderivatives. That's huge. You can't forget that. The area under a curve being related to the antiderivative is not an automatic give at all. That's why this is easy, because it's built on the backbone of a huge conceptual leap, that the antiderivative was related to the area under the curve. That's huge. Huge. All right. Okay. Anything else you want to look at? It's wide open. Nobody's asking, then you've got the floor. Yes?
Can we look over some things with left and right endpoints?
Sure. Let's see. Let's do this guy. and see how bad our approximations are. Now that we know the actual answer. So if I did a rough sketch of this, 2 minus x squared,
That is a parabola
parabola.
going
And
downward, I think.
I like it. So it's going to be here and go down. So at 1, where is it?
It is at
1. And at 3, where is it?
9, so it'd be -7.
Yeah. So going like this. So this is the area I'm talking about. Let me see what am I talking about. Okay. So you get a little rough sketch if I don't give you something so you can kind of draw a few rectangles if you need to. You really don't have to draw a sketch, to be honest, unless I ask you to. You'll do better. What's the very first thing I need to figure out? Well, the very first thing I need to tell you that I haven't told you is how many rectangles to use. So let's use 3. Because we're crazy. And let's do left endpoints. So what's the very first thing I need to figure out? The width. If I know how many rectangles, I can see how wide they are so they all kind of fit and cover the whole interval. So how do I find the width?
Thank you.
Cool. I like it. So that could be 2/3. So overall I get a 2, which fits in that interval. And then what else do I need to figure out? Using left endpoints. So the formula is going to be, for this specifically, it'll be I equals 1 to 3. I got 3 rectangles. And I don't know if you guys, I always do this on every problem I do. You can factor the width out. So it's 2/3 times the sum of the functions evaluated at the appropriate places. So what's the first place I want to evaluate the function at? 1, because I'm using left endpoints. So f of 3 will not show up because I'm not using the right endpoint. I got to stop there. So at 1, I'm going to have a rectangle, right? And how far up am I going to go? Yes, so 1 2/3. So this is 1 2/3. And then I'm going to have a rectangle from 1 2/3 to where? Go 1/3, and then go another 1/3. So from 1 2/3, go 1/3. That's 2. Go another 1/3. That's 2 and 1/3. All right, so now I'm going to go up to 2 and 1/3. I like it. All right, so I got, what was this? This is 1 2/3, 2 and 1/3. Am I doing this correctly, Jeff? Yes, I am. And then this is this guy. Arrow. Beep. This is a little funky because it's got some negative area. It's kind of hard to tell if it's going to be an over and under estimate. But let's see what happens. So what am I guess now I got f of 1 plus f of 2/3 later plus f of 2/3 later. And then whatever the hell that comes out to be, just throw that in the old calculator. I don't know what that is. Let's see. Thirds, 2 minus 25/9. Or 7/9, I think. Oh, I didn't do this. 7/3, 49/9, negative 31/9, I think. I don't know. I think 29/9, 2/3, negative 29/9. negative 58/27, whatever that is. What is it? Negative 58/27. Yeah, but what is that? Negative 2.140.
2.140.
All right. So if I did, so that's obviously going to be an underestimate. You know, as far as it's an overestimate because it's negative and under. And then if I did right endpoints, if I do right endpoints, what's the only real thing that changes? I want you, if nobody's noticed this, it'll make me cry a little bit. Instead of f of 1, I'm going to have f of 3. I don't use this, but I do use that. So I've already got most of the work for right endpoint done, don't I? So for right endpoint, it's going to be 2/3 times, what's f of 3? It's 2 minus 9, it's negative 7. So it'll be negative 7 minus 7/9 minus 31/9. So that's going to be a huge negative. All right, you guys, what's that? 63, 70, negative 101/9. I think. So if you average those, let's see. $44, 72, 130. What's 130 divided by 27? Anybody? You guys got calculators. 4.8148. And what's 14 divided by 3? It's negative 4.666. Yeah. So we got pretty close. What did I just do? I averaged these guys. Of course, remember that if you average the left and right endpoint, you kind of, one's an over and one's an under, and then together they make a decent. And it's that midpoint thing, too, that you guys did in the homework if you did the homework. Midpoint kind of averages each rectangle. So it's sort of like doing left and right and average all in one problem. Okay. Is that all right? Yes.
You know those integrals that have the abstract endpoints, where one endpoint is sine of x or something?
Oh, you mean take the derivative? Use the f-talk 1? No. As if, do you remember what?
Fundamental theorem of calculus, but it's not.
Yeah, it's got to be. So it's taking the derivative of the integral, right? Okay, it's got it. All right.
It's not substitution.
No, it's like this. Right? And then find the derivative. So a little thing here, this is not in the right form to use the rule for the derivative of an integral. Yeah, you got to flip these. It's supposed to have the x piece up here. And it seems minor, but it's the rule has constant to function of x. So if I don't do that, I'm wrong. So g of x, how do I switch these? Put a negative. And now I can take the derivative. No. I'm taking the derivative of an integral, so the thing inside shouldn't change. Whatever the integral would do to it, the derivative is going to undo that thing to it. So this will become natural log square root sine cubed x minus 1. But what rule comes into play? Is it just an x in my function? No, it's a sine x in my function, so I have to use what rule? chain rule. So this will be times the derivative of this. Close. Now, real quick, you guys, watch. I'm not going to do this, but this would equal the antiderivative of this evaluated at sine x, right? Right? Minus the antiderivative evaluated at 2. Are you with me? And actually, with the negative out front, it would be this, but screw it. Let me just add in. If I take this guy's derivative, now let me stop here for a second. Big ass f is the antiderivative of this. I don't know what the antiderivative of this is, but let's just say it exists. All right? There it is. If I take the derivative now, which is what I'm doing, what happens to this piece? This is just a constant, because it's evaluated at frickin' 2, right? So of course that's just a constant. And what's the derivative of big ass f? Little f. It's the original function back, right? Evaluated where? At sine. Now one thing I forgot, and then of course this has sine in it. That's the chain rule piece. That's the idea. If I did do the integral, I would then take the derivative, which would undo what I just did. It would come back to this function evaluated here, and the inside sine, so that would be cosine on the outside chain rule. So we're just kind of skipping that step of finding big ass f. Why would I if I'm going to bring it right back to what the hell it is right in my face, right? I'm not going to do that. Pick a number, add 7, subtract 7, multiply by 2, divide by 2. Why would I do shit? I'm not going to do anything. It's my number, 5. That's what I picked, man. I'm not going to do all that shit to it.
So would the derivative still would be negative if you flip the...
Oh yeah, I forgot a little negative, dude. Boop. Thank you. So the negative, and then this is here. I like it. All right, that's f talk 1. That's what it does. I still don't know if you guys are really cool with the fact that that is a function of x. For any given x that changes the limits of the interval, I get a different output. It's just a function based on an integral. So this is an area function. So what's the integral do? Find the area. So its outputs are related to the area between sine of the x and 2. That's the area between those two. Let's see. What else? Where else do you want to go with this stuff? Nobody wants to do a rotation problem? That's cool. So real quick, if I want to use disks, how does this thing look? Good, there's a pi out there because it's based on circles. So it makes sense that it's going to have a pi times r squared. Pi is a constant, that's why we write it out front of the integral so it doesn't mess us up. Just don't forget the poor little dude. Inside goes r squared. dx or dy, whatever it is. If I'm rotating around the x-axis, it has to be of course y-axis, and it will be y. Because that's how it's built. How do I locate my circles? I locate them on the axis I'm rotating around. Because as I rotate around it, I create a circle at that point. Whereas shells, how do I locate the rectangles I'm dealing with? So let's say I have, I got to rotate around the y-axis, let's say. So with shells, you gotta keep it. If you just keep the picture in your mind, the rectangle's got to stand parallel to your rotation axis. That's how you create the shell. So here I locate the circles along the axis I'm rotating around. That's why if I'm rotating around x, it's got to be dx, and vice versa. Shells, I locate the rectangles on the axis perpendicular to the one I'm rotating around, because they have to be parallel to it so they can rotate around and make a shell. Okay, I like it. So this would be based on the surface area of a cylinder, which was that 2 pi RH, right? So that's why it's 2 pi integral RH dx or dy. R is almost always x or y unless I'm rotating off axis, right? Like at x equal 1 or y equal -3. And h is going to just be the function. Or the difference if I'm doing like, so look here, what if I had, oh my God, what if I had an eraser that worked? That would be different. All right, I got nothing. Well, I'm not going to use that one. All right. So what if I had, let's do this. Let's do, if I had a function and then another function. I got it. This has been good. Too weird. All right. And I wanted to rotate that around the x-axis. How would my rectangles look? Would they be standing up or laying down? Laying down. Why? Because they have to be parallel to the axis I'm rotating on. So if I drew in a rectangle for myself, why did I put it there? I had to put it freaking somewhere. It's just a representative rectangle. How many rectangles do I have to choose from? Infinite numbers. I'm just going to pick one and put it on there. Right, so don't freak out on the little tiny insignificant details. Pick a representative spot to put something. How tall is that rectangle? Let me give these names. This is f of y. This is g of y. So what's the height of that rectangle? Because that's something I need. It's the height. What's the height of that rectangle? F of y minus g of y. I love it. So whatever those are, that's what I'm going to put there. What's this going to be? dx or dy? Why dy? Because we're going around the x-axis, and shells are perpendicular to that axis. That's how I find my rectangles. How do I find this rectangle or this rectangle? It's going to be at a certain y value. So I find them on the axis that's perpendicular to the one that I'm rotating around. It just takes a little thought to see why it makes sense. Less memorization, more why does it make sense, so I'll do that. Right? So you guys are like, none of this makes sense. And what would the radius be for this problem? And you could draw here's the radius here, up to this rectangle or up to this rectangle. What's the radius then? Y. I love it. Wherever the shit y, here's this representative y. Or, here, let's put it on an actual rectangle. So radius would be y. The height would be the difference between those two things. And then I would go from, it's all y, right? So I have to know what this is and I have to know what this is. Just figure out what the limits are. What might you have to do that? A lot of these problems are setting these functions equal to each other so you can see where they meet, right? Maybe. The problem I gave you on the practice test was a little banana problem. Whenever you have two parabolas that kind of both go up, you get these little banana areas. All right, so let's. Actually, I guess I didn't do a problem yet. Let's do a problem. I can't believe there's the one time I won it. Not here. The cleaning stuff. Oh well. So let's say I have. Let's see. like it. All right. Can you sketch a graph of that? So it's a region bounded by this function and the x-axis. So you don't draw the whole damn parabola. You obviously want to find out where that function. No, I know where it rotates, but I want to find out where the function hits the x-axis, because that's where it stops, right? That's the only part of it I care about. So what are you going to find for this? You're going to find its x-intercepts. Okay. So where are the x-intercepts? 1 and 3. And 2 would be where the vertex is. That seems to be a decent thing to figure out. So 1 and 3. The vertex would be at 4 minus 8, negative 4 plus 3 is negative 1. So there's a vertex. So there's a nice, complete picture. This is a little more evil than what I wanted it to be. And then the axis of rotation is x equals 1. So if I wanted to do disks, it would have to be integral d y or x. dy, because I'm going around something parallel to the y-axis. Do I want integral dy? Can you solve that for x? No. I don't want to. I don't want to. So no. Okay, so then we have to use what? Shell. So very often, not always, but very often I can eliminate a method so that I can focus all my attention on the other method. All right. What do I need to know? Is this still going? What do I need to know to be able to do shells? You're about to stop, are you? I don't know. We'll see. What do I need to know for shells? So the basic idea is this, and now we've identified as dy. So what's the height going to be? It's going to be a little bit evil. So this is my mistake. I didn't really mean to do this, but I can't have negative volume. This is an actual physical volume, so it's a little bit interesting. I want you to realize, if I had two functions, f and g, what would the height of a rectangle be? F minus g, right? Top minus bottom. So what's the height of this? 0 minus f of x. So the height's actually going to be negative f of x. I'm not going to give you a problem like that. It's a little freaky, but this is physical volume now, not representative volume. And the representative volume can be negative because it could be flowing or something one way or the other. This is physical hold in my hands volume. I don't want to get sucked into this black hole of negative volume. So the height is negative this. That's the height. What's the radius going to be? So here's how you do the radius. You ready? Where did I just put my rectangle? Right there. All right, so what's this? What's that value? What is it? What is it? X, 11. I kick ass. How far is at from this? How far apart are those? X minus 1. There's the radius, right? Radius is always bigger minus smaller in terms of the distance from the axis. So the radius here will be x minus 1. So what you want to do when you're studying is, for the disk method, what is important to identify. Get really used to what to identify, because then you can throw it into the interval. That should be the easy part. Shell method. what's important to identify. Identify them, throw them in, do the interval. Right? All right. And so now I throw them in. What's the integral going to go from to? We figured out it's d. What did I do? Why did I say dy?
Because that was for the reason. We might have been doing it was different.
Oh, okay, so yeah, this has got to be dx. I don't know why I put dy there. Dx, why is it dx? Because I'm going around something parallel to the y-axis. Oh yeah, I think I was talking about why it's not this. But around something that's parallel to the y-axis for shells is going to be dx then. It's always located perpendicular. Thank God, because everything in freaking x. So 2 pi. X's go from 1 to 3. That's nice. Radius times height. And I've lost interest. That should be easy. I just multiply that shit out. Integrate the polynomial. Not a big deal. I don't feel like doing it. I don't know if you guys understand. This is the very uninteresting part. This is still awesome calculus. But compared to this stuff, this is like, all right, just multiply it, do the antiderivative, throw 3 and 1 in there, whoop-de-doo. Doesn't mean you shouldn't. I'm not going to not take points off. You can't do the rest. The hardest part of these is getting here, though. Right? Figuring out what the hell to put in here. Okay. I don't know why I keep trying to do that. What if I were to take that same region and rotate it around y equal to 3? So the same region,